All right, the first question here related to wave physics from this paper one says, with which types of wave can the Doppler shift be observed? All types of wave. A, that's correct. Okay, all types of wave can we observe the Doppler shift in? Well, that's not good English class. We can observe the Doppler shift in all types of wave. A. 21. A distant star is receding from the Earth with a speed of 1.4 by 10 to the 7 meters per second. It emits light of frequency 4.57 by 10 to the 14 hertz. The speed of light is 3 by 10 to the 8 meters per second. The Doppler effect formula can be used with light waves. Well, that's kind of a nice clue about the previous question, right? If you're kind of debating that, oh, I only know about Doppler with sound waves only, but then it says the Doppler effect formula can be used with light waves. Nice little sort of reminder there. With what will be the frequency of this light when detected on Earth? This seems like a really good one because last Friday we had a nice little Doppler effect formula on the board, and now's our chance to put it to good use. If you don't remember that formula, just consult your notes. It should be in your notebook, right? So make sure that it's there. And if it's not there, add it in there now, right? So we're going to need it to solve this. We've got the observed frequency is going to be equal to the frequency of the source times the speed, the velocity of the wave. So if it's light, there's the speed of light approximately, divided by the speed of the wave. And then we either have to add or subtract how fast the source of the wave is moving. So the Doppler effect is all about how does the apparent frequency change based on the relative motion of a source and an observer. It could be an observer running away from, the source of a wave, or it could be the source of the wave running away from the observer, or they might be moving towards each other. All that matters is the relative motion. Are the observer, so with sound waves, it's ears, right? Are the ears and the, sound wave source moving towards each other or away? With light, it's eyes, right? So we see the light, the source of the sort of light waves has a frequency. Down in the denominator, we just need to sort of keep track of what effect that motion will have on the frequency. So let me explain once again how the Doppler effect kind of works here conceptually. You've got the source of a wave. In this case, it's a star, so it's putting out sort of light in all directions. And let's say the light from this star, and the star is moving this way, and here's Earth, sort of over here, pale blue dot. So the light from this star is spread out in all directions, and it's made it that far. But the star, remember, is receding, right? So it's moving away. So they give us sort of the answer to, okay, you could just memorize when things move away from each other, we're going to add in the denominator, right? So you say, okay, moving away, add, away, add. If they're moving towards each other, we subtract. Let's think about sort of why that works. And so now, this sort of black circle here represents where the light is mated from when the light was put out when the star was at this point. But a moment later, the star is going to be at this point because it's moving, right? It's receding. And so now the light from this point has made it all the way to here. And so I draw a circle sort of centered on this dot. And here you can kind of already see that the waves, the light from this one hasn't made it as far as this one, right? Because it just sort of got to that point, right? So at this point, the light has made it there. But it's still moving, right? It still has that sort of velocity vector this way. So now a moment later, it's going to be showed in blue. Now the light has made it sort of to here. And if we look at the two different perspectives, if we observe from over here, then we're going to see that these waves are closer together than they otherwise would be if this thing wasn't moving, right? They just sort of stay the same distance apart. So an observer on this side, when they're moving towards, is going to note that the wavelength is going to be shorter. And the wavelength and the frequency are inversely related. So the waves are going to sort of more frequently hit this person's eye, right? They're going to show up here, here, here. So if the wavelength is shorter, the frequency is higher. higher frequency when things are moving towards. That means mathematically, we need to subtract down here so that the frequency of the source is divided by a lower number, right? We're subtracting away the velocity of the source from the speed of the wave. That makes us divide by a lower number. Dividing by smaller numbers make our answer over here, our quotient, higher. So we know we're going to get a higher frequency when things are moving towards us, and kind of boils down to subtracting. Here on Earth, for this problem, the star is receding away from us, right? So here on Earth, as these light waves get to us, we're going to note that they're more spread out than they otherwise would be if the star wasn't moving, right? So here, the wavelength, the length between these sort of crests of the wave, let's say, is greater. It's not shorter, it's longer. So you get longer wavelengths when the relative motion between the observer and the source of the wave is moving away from each other. And that means we're going to add in the denominator down here. So longer wavelength means that the waves are less frequently occurring. We get a lower frequency. If we want the observed frequency here on Earth, we know it's going to be lower, okay? Then the way to achieve that mathematically is to add in the denominator here. So this equation, you could just sort of, memorize it. There's a way to express it in terms of wavelength also, but we have to know when to add and when to subtract. And so this keyword right here, starts receding from the Earth, means that we are going to add, right? We're going to add in the denominator. And so things move away, add away. What will be the frequency of this light when detected on Earth? So we're solving for the left side. It's already the subject, and we can just make some substitutions. So it tells us that the light is a frequency of 4.57 by 10 to the 14. So that's sort of in the visible part of the spectrum. We can see around frequencies of 10 to the 14. That's worth a nice little discussion to review those principal wavelengths of the EM spectrum. So we plug in this value for the frequency of the source. The speed of light we can approximate as 3 by 10 to the 8 over 3 by 10 to the 8. And then remember, we said we got to add, they're moving away, and the speed of the star as it's moving through space pretty fast, right? If the speed of light is 3 by 10 to the 8, this is 10% of it, 1.4 by 10 to the 7. So it's moving about 10% the speed of light. All right, so what will the observed frequency going to be? This is why we don't notice a Doppler shift with the light for things like here on Earth. It's true that like when a red race car speeds away from your sort of eyes, it becomes even more red. It red shifts as well because it's moving away from you. And so it's the wavelength of the light that's sort of traveling to your eyes is taking longer to get there. The same thing is happening, but if you add in, the speed of a race car to the speed of light, that really doesn't matter at all. So the slight change is going to be negligible, and you won't notice a redshift in like a car unless it's moving really close to the speed of light. We're not quite there yet with our technology. But for a star, in deep space, being carried away by the expansion of space is really what's going on in this. That's actually true. All right, so go ahead and get a head start on the calculation. Calculator ready. You guys solve the calculator exactly high form. Slide. All right, so we've got the frequency 4.57 times 10 to the 14. We're going to multiply that by the speed of light. So times 3 by 10 to the 8. That gives us a numerator of 1.371 by 10 to the 23. All right, divided by, let's see here, 3 by 10 to the 8 plus 1.4 by 10 to the 7. So I get 4.36 by 10 to the 14. I want to double check that again and just make sure I didn't make a button pushing error, but it seems reasonable because 4.57, and we know that the frequency is going to be lower because it's speeding away, and we get a lower frequency, 4.36, or we'd round that to 7, I guess, by 10 to the 14. So close to this answer, pretty close to this. See how these are all really close to each other? Let's just make sure we didn't make a computational error there in the denominator. So 3 by 10 to the 8 plus 1.4 by 10 to the 7. So that's 3.14 by 10 to the 8. The denominator there is 3.14 by 10 to the 8, right? Adding that. So 3 by 10 to the 8 times 4.57 by 10 to the 14 divided by 3.14 by 10 to the 8. 4.36, yeah. So that's correct right there. And so I think choice B is the best answer. A moment ago, I mentioned, oh, this frequency is like visible light. How could we sort of think our way to that? The speed of light is a constant. They gave it to you here. I'll give you the true value, 299,792,458 meters per second. And so that's close enough to 300 million that for most calculations, that's fine to just sort of round it up to 300 million, right? So it's 299 million. So that's in meters per second. The speed of light is always going to be the product of wavelength and frequency, okay? So if we know that the speed of light, and let's just round it now, 3 by 10 to the 8 is equal to the wavelength times the frequency, then let's go ahead and just divide by a visible wavelength. And so we can see between 400 and 700 nanometers. My favorite color is 510 nanometers. So I'll calculate based on that, sort of right in the middle of the spectrum, right? We see between 400 and 700. My favorite color is about 510, so maybe a little bit closer to the short wavelength end of the visible spectrum, but that's my favorite shade of green. 3 by 10 to the 8 divided by 510 by 10 raised to the -9. And again, it's like knowing, oh, nanometers, we can see in nanometers, and so that's nano. So 510 nanometers, that's the wavelength of my favorite color, green. And so the frequency of, sort of my favorite color is 5.88 by 10 to the 14. So you kind of see anywhere 10 to the 14, you're sort of around nanometer wavelengths. And so this would be just a little bit lower frequency, which means it might be more towards the red, orange, sort of part of it. Let's just calculate what's the wavelength of something with this frequency, right? Use the same equation, but instead of dividing by, this is the wavelength of green light to solve for frequency. Sorry, I don't have green ink. Let's figure out, what is the wavelength of this, just to practice this equation a little bit. So wavelength times frequency equals speed of light. Speed of light is approximately 3 by 10 to the 8 divided by 4.37 by 10 to the 14. That would give us our wavelength, right? Because we're dividing by frequency. So if I take 3 by 10 to the 8 divided by, open parentheses, 4.37 times 10 to the 14, that gives me 606.86 by 10 to the -7. That's the same thing as 686 by 10 to the -9, 686 nanometers. Okay, so that 10 to the -9, we can transpose with nano. So 686 nanometers is indeed within that visible part of the spectrum between 400 to 700. So, red light, that's somewhere around red, which makes sense for a star. So it's shifted from 4.57 down to 4.37, what if we calculated this with 4.57? Just a quick calculation, right? 3 by 10 to the 8 divided by 4.57 by 10 to the 14. So that's 656. So this shift is basically, it went from 656 nanometers when it was emitted, and as it traveled through, sort of space, because the light was, the source of the wave was speeding away from us, the light waves are arriving less and less frequently, right? And so instead of 656 nanometers, it's 686 nanometers. It stretched 30 nanometers. So from like an orange color to a more red color. So that's what happened to the starlight. Choice B should be correct. Good review on that one.